Hello, we are going to talk about some energy stuff that we need to do for Chemistry 10 that is not included in your textbook, but is included in your lab for this week, as well as a requirement for the course. So, electromagnetic radiation, as mentioned in the first video, is essentially light. And we just can't see it all. It has a large spectrum of things like microwaves, radio waves, all the way to gamma, X-ray radiation. We only see a small amount of that as visible light. But the speed of light, this is in a vacuum, meaning that this is not the speed of light in our atmosphere because there's air there, and air is not nothing. There's stuff in the air. So this is in a vacuum, like space. This is how fast all light travels in a vacuum. Now, your periodic table may have more numbers like 2.998 or 2.99 times 10 to the 8 meters per second, but you can also remember 3.0 times 10 to the 8 meters per second. It just depends on what formulas that you're given and what maybe you've learned from another class or what maybe you're trying to remember for long-term work. These are actually 2 video links that I will make sure that you have. And they are very interesting videos on what's called the wave-particle duality of light. So light can act as a wave, and light can also act as a particle. And this is getting into quantum mechanics and physical chemistry and all kinds of things that start to get really weird. And if you are interested in getting weirder, definitely check out the double slit experiment and reach out to me if you want to talk about it, if you're feeling that this is a little strange. But what happens when we get down into the very, very small is that we essentially stop behaving by Newtonian laws of physics. So it gets really interesting and strange, and the quantum world is incredible and wonderful and beautiful. But because of these weird behaviors, this gives us our probabilities of finding electrons in certain areas, right? Those different orbitals and shapes and all that kind of stuff. But there's another part of this about these waves that we want to look at. If you check out my slides, this is actually a moving thing. The little bear's waving. It's pretty cute. So identifying, first of all, a couple of things. So wavelength is one thing we're going to identify. And a wavelength is in meters or nanometers usually when we're talking about visible light. We're talking about light we can see. So these are our wavelengths. The wavelength is the distance between the 2 crests of a wave or the 2 troughs of a wave. So you can have a wavelength here as well. Wavelength is denoted by this Greek letter, and this is a baby lambda. Lambda. And so this just how long one cycle of the wave is. That's your wavelength. There's another term that I think I accidentally took the slide out of, which is frequency. So your frequency is how often the wave moves through a single point. So imagine that we're on a boat, okay, on this wave. There's our boat. There we are, there's a little hat. Okay, we're on a boat. And we are moving up and down this wave. If we anchor our boat, there's my anchor. If I anchor, then my frequency would be how often I bob up and down. If I am moving up and down a lot, I have a high frequency, and that corresponds to a high energy. If I'm not moving up and down a lot, right, I have a more relaxing adventure, then that corresponds to a lower energy. But we'll look at those relationships in just a minute. The frequency unit is per second. So per second. is going to be 1/seconds or inverse seconds. And then we have a unit for that called hertz. And you may be familiar with hertz if you've ever looked at your radio and seen that it says MHz, that is megahertz. That is the frequency of the radio waves that you're tuning into to listen to the radio. And just as a reminder, our visible colors of light, these different colors have different wavelengths, different frequencies, and thus different energies. And it goes in order from red of lowest energy to violet of highest energy. So lowest energy. And our highest energy color is violet. Highest energy. So thinking about this relationship, I want to add in a slide here. And I just want you to imagine a low energy wave. Maybe this is your low energy wave. And I want you to imagine a high energy wave. So how might I draw a high energy wave? Let me make it a little more evened out here. Okay, so there's my lower energy wave. Now, how could I do a higher energy wave? Well, I'm probably going to put more, like literally more energy into it, more waves in the same amount of space. Okay, so let's compare these two. If we're on our boat, okay, hanging out on this wave, we can think about what our experience would be like. I'm probably having a reasonable experience here, pretty good, right? I have a low energy. What is my wavelength like here? Thinking about the wavelength, look at the distance between the two tops of the wave here. This is a long wavelength. Which is lambda, which kind of looks like a wave a little bit, right? So low energy, a nice relaxing day on the ocean, a long wavelength. What is my frequency like? How often do you think I'm bobbing up and down in this scenario? So just imagine, we're in a nice relaxing situation. We probably have our bobbing up and down is going to be low. We have a low frequency. And that frequency, oh yes, I forgot to tell you, the frequency unit is going to be nu. So frequency is nu, which is like a fancy V. So our frequency is nu. Some textbooks will say F for frequency, but it is technically nu. Okay, so low energy situation. This is like red light. Okay, low energy, long wavelength, low frequency. Look at these L's. Low, low, long. Versus if I'm on this other wave down here, let's imagine we're on this wave. Our boat is on this wave here. If this is our situation, I'm probably not even on the boat anymore, y'all. My flag is way over here. I'm probably flying through the air. I'm probably not having a good time anymore. My hat's, tossed around over here. Okay, we're not having a very good time over here anymore because now we've entered into the high energy situation. So this is our high energy. Check out our wavelengths. What's going on with our wavelengths here? So I'll show you that you can do wavelength with the trough, the bottom as well as the top. So let's do a wavelength down here maybe. A shorter wavelength, right? Short wavelength. Just as a reminder, and repetition is key, writing that lambda again. So what's up with my frequency? I'm bobbing up and down a lot. If I'm just kind of thinking about this wave moving left to right underneath me, we're going to have also a high frequency, which is nu. Okay, so we got HSH or HHS or whatever you want to, SHH. So we've got our L's, low, long, and we've got our short and high. So what is the relationship like between energy and frequency? Just think about it. What is the relationship like between energy and wavelength? Direct or indirect? Meaning they both go up, but they both go down, or one goes up, the other goes down. So thinking about that, I'd like for you to pause and answer this question. Which wavelength of light has the highest frequency? So let's think about this. If I increased my wavelength, okay, that means my wave is going to be longer. My frequency does what? Goes down. Because if I have a longer wave, I'm not bobbing up and down as much. So if I'm looking for the highest frequencies, we're looking for high frequency. Would that mean high or low wavelength? That would mean low wavelength. So we will pick our lowest, our smallest wavelength. Think about it. A small wavelength versus a longer wavelength versus a longer wavelength. Draw them out if you want to in just comparison. Where do I get these numbers from? We can actually do calculations for this, and they're algebraic calculations. But in order to start those conversations about the calculations, we got to talk about that particle part. So we said that energy, electromagnetic radiation can act as waves and as particles. So particles are quantized packets called a photon. And Einstein came up with this. He said that, hey, I think that like the light can like act as a particle, it can package itself, right? So he called a photon a single packet of light energy, and the amount of energy in the packet of light depends on the wavelength of the wave property of the light. So they depend on each other. Oops, where's my other slide? Oh, okay, that's okay. So our yellow light has a longer wavelength than violet light. So tell me what you think about the energy. So think about what we talked about with the energy. So we have more energy with, so energy, higher energy corresponds to what kind of frequency? Corresponds to higher frequency, but we're bobbing up and down a lot, which corresponds to a lower wavelength. Write these things out for yourself. A lower energy corresponds to a lower frequency. They're directly related, which corresponds to a longer wavelength. So arrows can be really helpful in just visualizing quickly what's happening here. Okay, so yellow than violet. Yellow has a longer wavelength than violet. So yellow light looks more like this, and violet light looks more like this. Draw it out. Therefore, who has more energy? Well, imagine you're on these waves. This one here has way more energy. So violet has more energy. So B is your option here. Hopefully you chose that. So we're going to do one more thing, and this is actually in your slides, so forgive me that somehow didn't get put into these notes. We're going to look at the math. So there are two equations that we're going to look at for energy. So we know the energy of a photon, and Einstein and Max Planck came up with this together, or not together, but based on each other's work, is equal to something called h, which is Planck's constant, and nu, which is our frequency. And I'll identify what these are. So this is the energy of one photon. So if I give you a mole of photons, this E here is the energy per one photon. So think about it as a conversion factor. You can almost use this energy as a conversion factor. So energy of one photon. This is something called Planck's constant. These equations and this constant will be given to you on your periodic table equation sheet. But keep in mind that some instructors may want you to memorize these at some point. And here you have your frequency. The unit of your energy is going to be in joules. The unit of your frequency is going to be in hertz, which remember is inverse seconds or 1/second. How many times per second? So if you check this out with this constant here, it'll work out. So the units are actually pretty important to check your work. The other equation that we're going to use is C is equal to lambda nu. We're identifying here is the speed of light, which again will be provided to you. You can use 3.0, I'll use 2.998 because if I know more numbers, I definitely want to use them. Make sure that's very clear. Meters per second. This is my wavelength. And the wavelength must be in meters here because my speed of light is also in meters. I need that to work out. And again, this is my frequency, which is in hertz, but I like to spell the hertz out into inverse seconds or 1/seconds because hertz won't cancel, but the seconds will cancel if you look at the speed of light units. So here are two equations that you're going to be given. You'll be given your constant, Planck's constant, the speed of light. And we can think about these algebraically, where if you want, you can think about combining these. So a few ways to use these equations. Notice that, so just a couple things to notice. Notice that a common variable is frequency. My frequency, if I can find frequency in one equation, I can plug that frequency in and find another variable in the other equation. So I can use these two equations separately to solve some problems. If I need to go, for example, if I give you energy, but I want wavelength, they're not related in one equation, so I can find the frequency, plug the frequency in here, find the wavelength. Or you can do algebra and set them, set one of them equal to your frequency and write up a new equation. So if we want to do that, we can say, well, I know that to set up an energy. So what if I need to compare energy wavelength equation? What if I don't want to plug in and then get a number and then, solve it? But if I want to do an direct energy to wavelength relationship, which I don't have here. I have an energy to frequency relationship and I have a wavelength to frequency relationship, but I don't have an energy wavelength relationship. So let's take our C equals lambda nu and let's solve for nu. What is nu? Nu is C over lambda, right? Just by dividing lambda on both sides to get nu isolated. Now let's take this and plug it into nu here. If E is equal to H nu, let's plug our nu in. So then we get E is equal to CH over lambda. If this doesn't make any sense to you and you're like, why are you doing all this? You can absolutely just solve an energy wavelength problem by finding frequency in one equation and plugging it into the other. That's totally fine. But if you would like to do less calculator work, then you can combine these equations and rearrange and get a relationship between energy and wavelength here. Okay? If I wanted, and you need to be able to rearrange all of these, including this equation, if you want to use it, rearrange it for wavelength or rearrange it for energy or whatever it is that you want. But CH will always be constants given to you. So let's practice a problem. The wavelength of a sodium lamp sodium vapor lamp is 589 nanometers, which is a yellow light. What is the energy in joules of a photon of this light? Okay, so this is a little bit different. It's not dimensional analysis. We're going to identify kind of what we're given, identify some variables, and plug into some equations here. So I really like to identify what I'm being given and assign it a variable. So what is this nanometers? That's a wavelength. So I'm going to write wavelength equals 589 nanometers. Okay, that's the first piece of information. What is the energy in joules? So they're asking me energy equals question mark in joules. Now, I don't really need the problem anymore because I've written out what they're giving me and what they're asking for, and now I can pull down some equations. If you look on your periodic table equation sheet, you're going to see these two equations, C equals lambda nu, and E equals H nu. So you have options here. We have lambda, we can find nu and plug it in, and then find E. Okay, that's option one. So I can draw that path out for you. So option one would be plug in lambda, take nu, plug it in here, and then I get E out as my answer. Okay, that's kind of my path. Or I can do it all in one step. I can use E equals CH over lambda and solve for E. The latter is probably faster, but if you're not, this equation here is not given to you, so you have to kind of memorize it or rearrange it for yourself, and these equations are given to you. So I can show you both ways, but we do have to take care of one thing. So let's look at what our constants are. So C is going to be 2.998 times 10 to the 8 meters per second. And H is going to be 6.626 times 10 to the negative 34 joules times seconds. Do you see any issues with just plugging these numbers in? Hopefully you noticed these nanometers and these meters will not cancel. So I have to check my units. If your units don't work, it's not going to work out. So I'm going to have to take my 589 nanometers and I'm going to have to turn them into meters, and hopefully you know a conversion for that. So I know 1 nanometer is equal to 10 to the negative 9 meters. Maybe you have another conversion memorized. That's totally fine. We're going to get 5.89 times 10 to the negative 7 meters here. So that's actually the lambda that we're going to be using. So whichever way you're choosing to solve this, if you're going to use option 1, which is 2 equations, let me show you how I would do that. Option 2 is using 1 equation, and it's pretty simple. I'll show you that one as well. But try to work this out before you watch me work it out. So first, we're going to find our frequency from C equals lambda nu. So subbing in, or rearranging, and then plugging in. Meters per second over, use my meters that I found. Our meters are going to cancel, and we're going to be left with 1 over seconds, which is hertz, which is our frequency. So that's good. Make sure that when you're plugging this into your calculator that you're using correct scientific notation, formatting, and you should get 5.09 times 10 to the 14, 1 over seconds, or hertz, or inverse seconds, but leaving it 1 over seconds is fine. That's more helpful to see what your units are doing here. Then we're going to plug in nu into E equals h nu to find the energy of the photon. So E equals h nu, plug in. You'll see very clearly if you have hertz written, it's a little hard to see the units. So I usually will write it as 1/seconds. I can see that my units are going to cancel. Notice that I only did dimensional analysis one time here, and that was to get my nanometers to meters. But after that, I'm using my algebra skills to set these up and solve these equations. It really is about which of these you're more comfortable with, using the equations you're given, which maybe takes a little more time and work, or what I'm about to show you is when I rearrange the equations into one equation, I actually will have a lot less work to do. Option 2, one equation. And I get this equation because I can set C equals nu lambda to nu and then plug nu in. So if you see what I did here, this is where I'm getting this equation from. And if again, you look at this and you're like, I don't know what you're doing, stick with option 1. Option 1 is given to you. Oh, whoops, I put the wrong thing. This is supposed to be my lambda. So I'll plug in my speed of light, meters per second, times my Planck's constant, which you will have given to you. You'll not have to memorize these, at least not right now. All over my meters wavelength, not that nanometers. That's the biggest mistake I see students doing here is that we are doing our nanometers. There's my unit canceling just to make sure I'm going to wind up with the unit that I want. And I should wind up with the same thing. In a lot less time, probably. But it depends on how much time it takes me to develop this, right? So this is pretty much the extent of what you're going to be asked. Now, remember that this is really 3.37 times 10 to the negative 19 joules per photon. So there, this actually can become a conversion factor and be used in dimensional analysis to figure out the amount of energy in a certain number of photons. So be aware of that. But as far as the algebra goes, the new stuff goes, this is pretty much it.